Hi, let's take a look at the second assignment in COIS 4550H. So question number 1. This is a one-dimensional cellular automata. So what we're looking at here, this row is the starting position, starting generation. This is the next generation, and this third generation hasn't been completed yet. So you're asked to come up with a rule set which turns this first row generation into this one. So this is actually pretty easy. Keep in mind in a one-dimensional cellular automata that according to this rule set, the cell in question's value in the next generation is based on its left neighbor and its right neighbor in the current generation. So let's take a look at these three. We've got 3 zeros. 3 zeros, and the cell in question is the one in the middle on the next row down, this one. So these 3 zeros have generated a 0, so we can just fill in a 0. For the rest of them, I don't want to give you the answer, so let's just add a few more dots here. Take out a dot or two. And see what the rule set is for this set of Okay, so let's move along. So we've got 0, 0, 1. So 0, 0, 1 gives us a 1. So 0, 0, 1 gives us a 1. So we move along. We have now 0, 1, 1. 0, 1, 1. 0, 1, 1 gives us a 1. So 0, 1, 1 gives us a 1. Then we move to the next generation. So we've done 0, 1, 1. So now we have 1, 1, 1. 1, 1, 1 gives us a 0. Keep moving along. We've got 1, 1, 0. 1, 1, 0 gives us a 1. 1, 1, 0 gives us a 1. We've got 1, 0, 1. 1, 0, 1 gives us a 1. And then we've got 0, 1, 0 gives us a 1 as well. And then finally 1, 0, 0 gives us a 0. So this is the set of rules. You're also asked to fill in the last row using this rule set. So 0, 0, 0 gives us a 0. 0, 0, 1. 0, 0, 1 is a 1. So we put a 1 here, or a dot. We've got 0, 1, 1. 0, 1, 1 gives us a 1, or dot. 1, 1, 0. 1, 1, 0 gives us a 1. We've got 1, 0, 1. 1, 0, 1 also gives us a 1. We've got 0, 1, 1 gives us a 1. We've got 1, 1, 1 gives us a 0. We've got 1, 1, 0 gives us a 1. And we've got 1, 0, 0 gives us a 0. And then the rest are all zeros. So this would be the next generation. You're also asked whether or not, or what class that this CA would be in. Is this boring? Boring means it turns into all zeros or all ones. That doesn't appear to be the case. Is it stable, meaning it's not going to change from one generation to the next? The same ones will be on or off. That's not the case. Chaotic or complex. So we're going to try to look for some sort of pattern here. If there's a pattern, it would be complex. If there's no pattern, it's chaotic. In order to do that, you should run through another couple generations and try to determine whether or not this looks ordered to you or not. So that's the first question. Question number 2. Deals with a Turing machine. So remember, in a Turing machine, we have an infinitely long tape with characters on either zeros or ones or blanks. In our case, we don't need to worry about blanks because we're told that at the start, the tape has all zeros on it. So it tells us to start in the middle. Let's start here, and we're in state A. So if you're in state A and you read a 0, you write a 1. So we would write a 1. We move right, so now we're here. And we move to state B. So in state B, if you read a 1, you write a 1. You move left and go back to state A. So what you've got to do is follow this through until we reach this halting state, and then tell me what it is that you see and describe the movement of the read-write head. Question number 3. This deals with two-dimensional cellular automata. We have here the current generation. This is a set of rules. This is the game of life with an addition. It says if the number of odd neighbors is exactly 3 or exactly 5, then the cell will be on in the next generation regardless of its current state. So what you've got to do is check out all of the dots and the dots around them to see whether they're on or off in the next generation, which you'll write here, and the third generation you'll write here. So let's just take out some of these so I don't give you the answers. And we'll look at this. So we can start with the ones that are currently on. So this dot here, this cell, has one neighbor on, so it'll be off in the next generation. This fella here, he has 2 neighbors on, so he'll be on in the next generation, so we put a dot here. This one has 1, 2, 3 neighbors on, so he's guaranteed to be on in the next generation. This fella has 2 neighbors on. He keeps the same state, so he's on. And the same as this fella, he has 1 here and 1 here. What you've got to do next is check the surrounding cells. Let's say this cell has 1 neighbor on, it stays off. But this one here has 1, 2, 3 neighbors on, so this cell is actually on in the next generation. This one has 1, 2, 3, 4 neighbors on. He's off in the next generation. This one has one neighbor. So it looks like the only one that we're going to add is the one here that had 3 neighbors on. And then you move to the last generation, apply the same set of rules, and tell me what it looks like. So that's question 3. Question 4 is the Margolis rule. So in this one, remember, we use blocks of cells. So let's say we're looking at this block, start in the top left corner. So what we need to do is to look at the different configurations. You'll see the rule here. So this tells us if it's currently in configuration 0, it goes to 15, 1 goes to 14, 2 goes to 13, 3 to 12, and so on, until finally configuration 15 goes to 0. So let's look at this cell in the corner. We've got these 3 on. So if you come down here, this is it here, this is 13. So we come back to our rule set to see what 13 changes into. We've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 changes to 2. So we see what 2 looks like. This is 2. So the next generation, this cell is going to look like this. So just do that for all the other blocks and come up with the diagram for the next generation. And then you're asked, is the rule reversible? In order for it to be reversible, there only has to be one prior generation which could generate the current generation. Finally, the last question is your discussion question. This is try to come up with some new ideas as to what applications there are for cellular automata. In the notes, I mentioned lots of possible uses. I want you to think about some of those, comment on the uses, and try to come up with some new uses for CAs. There's lots and lots of uses for them. So I want you to post one in response to these questions and then one in response to another student's post. And please end your post with a question in order to try to stimulate our discussion. You should make your first post before Module 2 ends, and then you've got another week to respond to the other student's post. If you have any questions, by all means, send me an email. But this is an overview of the second assignment.